Until now, you have learned how to express a straight line by its equation y equals mx plus c. But you can also do this using vectors. For that, you have to find the position vector for any arbitrary point P that belongs to that line. So I've represented here a straight line in blue, and the idea is for us to find the position of any point P that belongs to this line. So what do we need? We need first to define the direction of the line, and then also lock it in place at a certain position. So let's first take care of the direction of what we need. This can be done with two position vectors defined by 2 points A and B that belong to the line. Okay, so I've chosen this point over here, A, and this point over here, B. As you already know, if you have 2 points that belong to a line, to any line, this will define its direction. Okay, so what are going to be the coordinates of the position vector OA? Obviously, it's going to be XA, YA, and for OB, it's going to be XB and YB. So now we have the direction vector of the line is given by AB, as you already know, and this can be calculated doing OB minus OA, as I've mentioned in a previous lesson. Okay, with the coordinates, that will be it. So we now have the direction, but the direction can be this, and the position be anywhere. So we need to lock it in place. Okay, so for that, we need a specific position vector. In this case, I'm going to use just this vector over here, or OA. All right, if I define this vector OA as one that ends up in the line that I want, then the line is going to be fixed there. Okay, it doesn't need to be OA, but for the purpose of this, I'm going to use the vector OA. OA has coordinates, as you saw, XA, YA, so the position vector of any point P belonging to the line can be defined as the sum of the position vector OA and the multiple of the direction vector AB, defined as lambda AB equals lambda times xb minus xa for the x coordinate and yb minus ya for the y coordinate. Mathematically speaking, the position of a point P, the position vector OP, is going to be equal to OA plus lambda AB. Let me go back to the drawing to explain what I mean. The position vector of this point P, random, is going to be given by OA plus a multiple of that, AB. Make sense? The value of lambda, that is the multiplier that you use over here, is going to define the exact position of P, as we're going to see over here. It's easy to see that if lambda is 0, if this is 0, then OP is just OA, okay? And the point P is going to be the point A. If lambda is 1, then this is going to be 1, and OP is going to be OA plus AB. So OA plus AB, that's point B. If lambda is somewhere in between 0 and 1, this means that the point P is going to be itself somewhere between points A and point P. If lambda is smaller than 0, then this is going to be a negative vector, meaning that the point P is going to be below point A, somewhere over here. And if lambda is bigger than 1, then the point P is going to be above P. Note that any point belonging to the line can lock it in place, but this brings different values of lambda for each different point. Makes sense. The value of lambda is dependent on which one you pick to be the vector that locks it in place. If you would pick OB, for example, then the lambda would be different for the same value of P. Okay? General vector from the equation of the line. Let's get to the equation of the line in vector form. Okay, so let's say that P equals a position vector OP, A is the position vector OA and B is the position vector OB. Okay, so as we saw, OP equals OA plus lambda AB. I'm going just to write this down in component form, and here you have it. Okay? What am I doing now? I'm just multiplying the lambda by the two values over there. Okay? So this is going to be equal, everything else is the same. So this is going to be equal to lambda xb minus lambda xa, and over here lambda yb minus lambda ya. I'm going now to separate this so that I have the lambda xp, lambda yb, I'm going to put over here, and I'm actually going to bring the lambda back outside of the column form. And I'm going to do the same to this minus lambda over here. I'm expressing it right over here. So minus lambda xa ya. Why am I doing that? Because now I have here two vectors with the same coordinates, and I can factorize that. So I'll have 1 minus lambda xa ya plus lambda xb yb. And what is this? This is OP, this is OA, and this is OB. So you have here the coefficient for this vector, so to speak, which is 1 minus lambda. For this is lambda. And if I want to express this in simpler terms, using the notation that I used here at the beginning, then this would just be b equals 1 minus lambda a plus lambda b. And here you have the vector equation of a line.